All right, it's time for day 9 of Advent of Code 2024. Let's lock in. Today went a bit slower than I thought it would. It took me 6.5 minutes for part 1, which is pretty good, and 24 minutes for part 2. So the recording's going to be quite long. I hope you didn't get too bored watching me solve stuff for 24 minutes. But let's go to part 1. Today we're dealing with some file systems. So we are given a list of integers as a string, and this represents a disk. So what the numbers mean is they describe the blocks in the disk. Some of the blocks contain files, and some of the blocks are free space. So the first number tells us the amount of free space, the amount of blocks that are files at the beginning of the disk. And then the next number is the amount of free space, and then the next number is the amount of files, and so on and so forth. So it alternates between files and free space. So in this input example, 2, 3, 3, 3, 1, 3, 3, etc., we have 2 files, which are ID 0, 3 free space, another 3 files, which are ID 1, 3 free space, and then 1 file, which is ID 2. Basically, every time you have a file, contiguous file block, you increment the ID by 1. So this is the actual uncompressed file structure. Our goal, or rather the amphipod's goal, is to make more contiguous free space by compacting all the files. So we need to move some files around such that there is more free space at the end of the file. Essentially what we're going to do is we're going to start at the end of the file system, take a block that has a file in it, and then move it to the first free space. And now the last block is empty, so now we move back, and this one has a file in it, so we're going to move that back as well, and so on and so forth until all the files have been moved towards the beginning of the file. Let's go through my code. How did I implement this? So first, we need to do some input parsing. We need to convert the line, which describes the compressed file system, into a list of the actual file system. So I have this function here that takes in a string and makes a disk map, so the uncompressed file system. We start out with an empty list of blocks, and then we iterate through all the numbers in the input. We have 2 variables that we keep track of. The first one is file, so whether the current number describes a file or free space. And the second is the ID, which we just increment as we create new files. So we just iterate through the entire list, get the number, which is the number of contiguous blocks it represents. If it's a file, then we used the Python list multiplication thing to append a bunch of non-empty blocks at the end of the current file system. That's going to contain the file with ID. We're going to increment the ID and then say, well, the next number is going to tell us the number of free space. So is file set to false? If is file is set to false, then we need to add some free space, which I represent with the none value. And now we have the actual iteration. So move is a function that takes in this uncompressed file system and then moves all the files at the end towards the beginning. So we need to first find out how much free space we have at the very front of the file system, and as we move blocks forward of files, we're going to move the free pointer forward so that we know where to insert the next file. Notice that this variable, first free, will never decrease, because as we fill up first free, it'll only move to the right to discover more free space. We're also going to have a second variable, I, which tells us which index we want to move. So I is going to start out at the first value, first index that contains a file, and it's going to iterate backwards. So essentially you have a 2-pointer thing. The first free variable is an index that tells us where the first amount of free space is, and I is the index of the very last file. So these two are going to slightly converge, and as they converge, we move the data from I to first free. That transfer is done in this for loop, so while the 2 pointers have not converged yet, we swap the values. We take the data from the last index and move it to the first index, and then we empty the last index, and then we just find the next amount of free space using this while loop. At the end, we have to compute a checksum. So this is how we extract our answer. Once we have the final file system, we take every instance of a file and multiply it by the block index that it's at. So this 0 would be multiplied by 0 because it's index 0. This 9 would be multiplied by 2 because it's at index 2. So we do 0 index the file system, which I'm very happy with. And then you add all of these products together. For part 2, we have decided to move entire files at once. So before this, in part 1, we're just moving one block of data at a time. This time, we want to avoid file system fragmentation, so we need to move all files at once simultaneously. At the beginning, for example, we have these 2 9s. We want to move it towards the front, but we can't move them one at a time. We have to move them both at once towards the beginning. And we're going to start from the highest file ID and slowly go down. And if there's no free space where we can insert this file closer to the beginning, then we just skip that file ID. This took a lot of work to debug, or rather it took a lot of time. It's not too complex of an idea, but just the implementation details are quite difficult. So this is the same function, make file system. I explained this earlier in the video. In part 1, we just take in the input string and then create a list of all the file IDs as well as blank spaces. Probably didn't have to do this, to be honest. You could use a more compact system, but this made things more explicit for me to think through. I also have this utility function that we don't need anymore that takes in the uncompressed file system and just prints it out. This was useful for tracking as I debugged the program. Well, there is one modification, however, that I made, which is 2 arrays, size and lock, that keep track of the size and the location of each file. So as we make the file system, that's why I put this global lock size here, so we can keep track of where all the files are, as well as their sizes. We update these arrays as we iterate. For every time we create a file, we want to keep track of its location, which is simply at the very end of the list we have so far. So just the length of that list is going to be the index at which we insert the new file. And we also want to keep track of the size of the file, which is simply the character in the input. So that's very important as we move on to the move function, which is the same as in part 1. We just want to compute what happens after we move all files towards the beginning. So big is a poorly named variable that describes the highest file ID. Probably could have done that in make file system, but this was easy to implement. Basically, it starts at 0, and we keep incrementing it while the file ID has a non-zero size. The problem tells us that we want to start from the highest file ID first, so we start from big, and then we increment backwards to -1, because Python ranges are not inclusive, so we want to make sure we catch the 0 file. It's probably not that important because 0 is going to just get inserted at the beginning anyways, but for completeness sake. And then we iterate the file ID that we want to move down every step. So say we want to move file ID 9 backwards. We want to find the first instance of free space that is at least 2 blocks wide. How we do this is with some more for loops. So free space and first free are 2 variables which are going to get updated to track where the first block of free space is. Initially it starts at 0, and we're going to say we have no free space. We want to make sure we have enough free space to fit our file, and this is where the size array comes in handy. We know the size of the file that we want to move. We want to make sure that we have enough of it. So while free space is less than that, while we don't have enough free space, we want to allocate more. And how we do that is basically we go to the next instance of free space, because currently, say we have a contiguous block, but it doesn't have enough space. We want to jump to the next one. We increment first free, which is the index by free space, so it jumps to the end of the contiguous block that we have right now, and we reset free space to 0. We're going to probably run into some more files, so these blocks are not going to be empty. While it's not empty, we want to increment this index by 1 to find the first index past our current block where there is actually free space. And then while we're not hitting the end of the file system, and while we have empty space, we increment free space by 1. So in theory, by the end of this for loop, one of two things will have happened. Either we hit the end of the file system, in which case that's bad and we don't have enough free space, or we do have enough free space. So that's with this check. We check if the index is greater than the location that we have our current file at. If so, then we can't move the file later to find more free space. That's not something we want, so we just actually, that's not necessary. None of these 2 lines are necessary. I had them previously because I had a while loop, but essentially we just want to move on to the next file ID to move. So now, if this is not the case, then we do have a contiguous block of free space that we can move the current file to, and we just use these 2 for loops to swap the blocks. There's probably something more efficient we could have done by like splicing arrays, maybe, but we just go through the current contiguous block of free space, assign all of those to the file ID that we want to move, and then go where the file originally was and erase all of those to be none. At the end, the checksum function is still the same. We go through all the indices of the array and just multiply the file ID at that point times the index, add all of those up, and we get our answer. So that's it for day 9 of Advent of Code 2024. If you want to check out my code, it'll be linked to in the description. I have a GitHub repository where I link the code to all of the day's puzzles. If you have any questions or comments, feel free to leave them down below. Thanks for watching, and I'll see you tomorrow for day 10.